Hello and welcome to another day of Advent of Code. Today is day 13, which part 1 is pretty easy, and then part 2 is, well, if you don't know the math like I didn't know the math, part 2 is pretty hard. But anyway, let's jump into it, and I'll hopefully explain and hopefully make it so you can understand how part 2 works. So let's jump into it. Okay, so the problem today is our input is given as one line with a timestamp, and we'll use this timestamp for part 1, but not for part 2. And the second line is a list of buses, which are going to be integers for the bus ID, and it'll be X if they're out of service. So if you look at our parsing, this is an example of one of the inputs. And for part 1, the bus ID, or no, that's still the same. The bus ID is how long the route is. So if this is our bus ID 7, that means that it'll appear every 7 timestamp units. So it'll appear at 0, and then every part after that. All the buses start by departing at 0. And the answer for part 1 that you're looking for is the first bus ID that appears after the given timestamp. So given the timestamp 939, which one of these bus IDs is going to appear directly after that? And then we're going to multiply that bus ID by how long it appears after that. So, if it appeared at 942, that would be 3 units after this, and say it was bus 59, 3 times 59 would be whatever your answer is. I don't think that's actually the answer. We will compute it. But that's how this answer is supposed to work. And part 2 is a lot more complicated. The idea behind part 2 is it's a special promotion, and I've tried to summarize what it looks like here. Basically, since all the buses depart at a particular time, you're looking for a very, very special timestamp where each bus appears in order at the nth position. So basically, bus 0 will appear at that timestamp. The next bus, so this one here, will appear at that timestamp plus 1. So it's kind of like a diagonalization sort of deal. This bus is out of order, so we actually ignore bus 2 here. Same with this one here. But this would be, let's see, 1, 2, 3. This will be, this bus should appear at timestamp plus 4, and then 6, and then 7, etc. for your entire input. And yeah, figuring out the actual algorithm for this part is a little bit tricky. We will get to that when we start talking about part 2. But let's do the parsing first, since I think that part is, at least easy and at least gets us started with something. So what I did here is I took my input and I split it into 2 different lines for part 1. Part 2, we did it a little bit different. So we have line 1 and line 2 equals s dot split lines, and we're going to return int line 1. So that's the first part of this, convert the first line into an integer, and then we need to convert the second line into the bus IDs and ignore the x's. So we can do buses, which, is it 1 or 2 s's? I don't know. We're going to use 1 s for this video. I used 2 s's on stream, but I don't know what's actually correct. We're going to do int bus for bus in line 2 dot split, comma, and we're going to filter out the ones that are just x. So if bus does not equal x. So this should filter us just to those integers. Do buses here. And for part 2, the output is a little bit different. We actually, I guess we can still use this, but we actually don't care about line 2. So we can just ignore it. But for the second one, we actually need to keep track of the index for each of the buses, even if we filter them out. And so what I'm going to do here is I'm going to use enumerate. And that will, actually, let's put this on multiple lines so it's a little bit easier to read. And this will give us 4 I comma bus in this. Again, we still need to filter if they're based on x. But now we're also going to keep track of the position here, which is going to be I. We can actually just call this position. That way it's a little bit more readable. And so this is how you would parse part 2. Let's actually run this, make sure it works. Parsing.py. Here has no attribute. Spit lines. Yeah, we got a rapping S who is spitting lines here. There we go. Okay, so for part 1, we parse timestamp is 939, and we get 7, 13, 59, 31, 19 for the buses. And for part 2, we get 7, 0, 13, 1, 59, 4, 31, 6, 19, 7, which is what we expect. Okay, so the parsing's out of the way. Let's start working on part 1. Let me actually open this up again, just so that I have that ready. Part 1. And I've already put the, the thing that we parsed here, and we're going to make a function that takes the timestamp and the buses. So when I thought about this, this is kind of a minimization problem. So I'm going to try each of the buses in order and see which one is going to appear the soonest. And so we can figure out like where it's going to appear right before the timestamp by using integer division. So let's first do the first bus. That way we have a baseline minimum. Minimum time, I guess like number of times the bus comes, times it comes equals TS divided by buses 0 plus 1. So this will give us, if say the number was, I don't know, 20 and the bus ID was 6, the bus would come, or this 20 integer divide 6 would give you 3, 3 plus 1 would be 4, and so it would loop 4 times before you would get to that thing that's after the timestamp. And so that makes our minimum time times it comes times buses 0 times. So this is like the minimum timestamp. And we also need to keep track of the bus ID in that case as well. Bus ID equals buses 0. And then we want to loop over all the rest of the buses and see if anything beats this minimum here. So for bus in buses 1 colon. So we're looking at every other bus except for the first one. And so we're going to say times it comes. I'm actually okay to clobber this variable up here because we don't actually need it. This is just to simplify this expression here. I could have really just inlined this here. Oops. One. Yeah, so you can imagine that this is just inlined here. But well, we'll do that. That makes it easier. So candidate time equals timestamp divided by bus plus 1 times bus. And if candidate time is less than minimum time, then minimum time equals candidate time and bus ID equals bus. So that allows us to compute our minimum. And then what was the final thing that it wanted to do? Is multiply the bus ID by how long it appears after the timestamp. So we're doing return bus ID times minimum time minus timestamp. And so that's kind of our answer for part 1. Make sure that's the right thing. Part 1, and we get 295, which is what we expect here. Cool. If we look at algorithmic efficiency here, again, this is pretty simple and straightforward. This is ON. We're going to have a hard time computing it for part 2, though. But anyway, let's start with part 2. So I didn't know the math behind this, and when I solved it on stream, a bunch of people in chat helped me out to figure out the actual math. I'm not going to skip you ahead to the math cheaty solution. I'm going to show you another way to solve it, actually 2 other ways to solve it. One of them where you actually don't even need to know anything about the problem at all. The first way we're going to solve it is by using a tool called Z3, and what Z3 is actually, let me just open up Z3 solver GitHub so I can show you what Z3 is about. The idea behind Z3 is a very fancy theorem prover framework thing, but the TLDR of it, they have an example down here. They don't have an example down here, but anyway, I've used this in previous Advent code years, but the Z3 is absolute magic. Essentially what you do is you tell its solver a series of equations, you describe the you describe the solution space, and it will tell you first whether it's possible to solve it, and then 2, it will give you an example of a solution for that. So all you have to do is tell it about the problem in a specific way, and you don't have to know the math, it will do the math for you. So I thought this was pretty cool, so I went ahead and tried to solve this first with Z3. I failed miserably, but after stream I tweaked with it a bit and eventually found a solution that works. It turns out in usual cases with Z3 you can give it all the equations at once and it'll just kind of figure it out. But with modular arithmetic, which is what we're dealing with today, Z3 isn't as good at solving a system of modular equations. So what we'll do is we'll break it down into a bunch of smaller equations that Z3 can solve for us. And to get started with Z3, we're going to make a virtual environment and we need to pip install z3 solver. I'll show you another solution after this that doesn't involve z3 and just is, you know, normal Python loops. That'd be part 2. But we're going to do from z3 import solver and from z3 import int. What int is going to allow us to do is define variables and placeholders, and it will allow us to kind of figure stuff out after that. Okay, so also I've put some smaller examples here so that we can kind of work them out on our own and look at how these work. I'm actually going to talk you through these first, and then I'm going to show you how I did it with z3, and then I'm going to show you a loop. Okay, so I created this test case and this test case here just so I could show you for this video. But you can imagine the buses could have been 5 and 7. One thing that I noticed about all of the numbers in this is they are all prime. And this gives us some interesting qualities. Notably, we don't have to deal with lowest common denominator, or least common multiple. Least common multiple. I mixed up GCD and LCM. Sorry, least common multiple. We know that we can get some repeated amount of... we'll see the same repeating pattern between two numbers just by multiplying them together. So for instance, you know, if we find a pattern that happens at 20 in this case, which is where, you know, 5 has 4... there's 4 5s that get you to 20 and 3 7s minus 1, which gets us 1 down, which is our answer here. We'll see that pattern if we add the multiplication of these two together. So if we add 35 to that, we'll see the same pattern at 55, which is what? 11 times 5, and 8 times 7 minus 1 would get you 56 minus 1. So you'll see the exact same pattern repeated based on a multiplication of these two factors. And we'll kind of use that fact to build up our solutions. You'll notice here that we do the same thing, but we extend it one further. So we see, you know, we get 20 for our first answer with 5 and 7. And if we want to find our next answer, which adds another factor here, we'll use our first answer and then add that, you know, that looping factor, that 5 times 7, some number of times to get us an equality with a factor of 9 subtracted with 2. And so in this case, you know, 20 plus 35 times 4 gets you 160, which is the same as 9 times 18, or 162, minus 2, which I think of in my head as 90 plus 72, but anyway. And we're gonna use that to implement our solution. So let's do this with Z3 first. I'm a little rusty on Z3. I've only used it once before on a different advent of code problem, so I'm actually gonna be looking. I have a little cheat sheet off screen, so usually I do these advent of code puzzles re-recorded live, but today I'm gonna be cheating a little bit, so apologies for that. Okay. But first we're going to tell Z3 about our variables. We're going to have basically 2 variables here. One is going to be our timestamp. We're going to build a bunch of equations based on our timestamp. The other is an unknown multiplier, which is kind of, you know, this multiplier here, or this multiplier here, or here, depending on where you want to think about it. So we're going to make t equals int. This is all you have to do to tell Z3 that it's some integer variable. And we're going to have another integer variable n. Now, we're going to kind of iteratively build up this timestamp value here. So you can see, like, this first loop where we just look at 2 numbers, we started at, well, you can actually imagine a 0th loop where we start at, you know, t equals 0, and the multiplier here is our first value is 5. So we can say mult equals 5. And so you can imagine it's 0 plus some number times 5 is equal to some number times 7 minus 1. Yeah, so we're gonna start with t equals 0, and we're gonna start with our multiplier is equal to our first parsed integer. So that's gonna be parsed 0, 0. And now we're gonna loop over all the other ones and try and build up a multiplier and add up a t here. And so we're going to do for bus position in parsed 1 colon. And we're going to build a solver here. So solver equals solver. This is how you kind of, you build a solver, you add equations to it, then you say solver.check, and this will return either satisfiable or not satisfiable. We're just going to assert that everything is satisfiable here. If it returned unsatisfiable, that means Z3 doesn't know how to solve it. Or it's provably unsolvable, or there's a bug in Z3. So for instance, when I was doing this on stream, Z3 kept telling me that this problem was unsatisfiable, but that was because Z3 didn't understand mod in the mode that I was using it. And then finally, we're going to retrieve the value out of this. We still haven't done the equations yet. I'll do that in a second. We're just doing the Z3 boilerplate here. And for that, we'll do t equals solver.model. The model is where the solver will spit out some solution for this, and you can index using one of the variables you had above, and that will give you its value out. But our series of equations here, and we can add them one by one. The first is we expect t to be greater than 0. This is just so it doesn't just spit out 0 for the trivial case, because the bus has to do at least one thing. The other equation that we have here, solver.add, is that t plus offset is divisible by the number of by the individual bus ID. So, you know, the periodicity of this bus is the timestamp plus whatever offset, and we can represent that by saying t plus offset mod the bus is equal to 0. And again, I'm just basically putting expressions in here. The solver is doing some magic behind the scenes to figure out what's going on there. The last condition that we need to add here is kind of our iterative condition. So we need to basically take our previous answer and add it into here and make sure that that is moving forward. So we would do solver.add t is equal to, so our timestamp is equal to the previous timestamp. T0 is 0, but you can imagine T1 being 20, or if we took this one layer further, it'd be further. T plus some variable n times our multiplier. And so, like, you know, in this first version, it's 0 plus some n times 5, and Z3 is going to figure out that this n is 4 for us. We don't even have to tell it what this n is, just that it is some value. We actually don't care what it is as well. We only retrieve out the timestamp value after this. And that's the solver portion of it. That's basically it. You just tell Z3, you know, these are the scenarios. Figure it out. But we do have to do one more thing here. We have to build up our multiplier after each loop. So we'll do times equals bus. That way we continue to build up that least common multiple there. And then finally at the end of this, we just return t. And this might seem way too magical. I agree. So I wanted to learn this better and better. Where is my syntax error? We have a parenthesis missing somewhere. Where is it? I think PyPy will tell me. Parenthesis never closed. Oh, this print is never closed. Which means this one is never closed. I always find that PyPy gives a better error message here than this one. This error message is just like, okay, cool, thanks. I have no idea what's going on here. No module name Z3. All right, I need to activate my virtual environment. Offset is not defined. Oh, I called it position here. I called it offset in my other solution. And you can see that it computes those 3 values for us. Oh wait, this one's wrong. Did I typo this? I bet I typoed this. Oh yeah, this is supposed to be 6, and this is supposed to be 7. Cool, now it gets us the right value. I copied the input from the other problem incorrectly. But yeah, that's basically the Z3 solution. Again, I didn't have to figure out the math here. I just like told it some system of equations, and it figured out the rest for me. Let's talk about how to implement this if we don't want to use Z3. So I took a little bit of understanding further and, you know, turned this Z3 solver into a special loop. So let's look at how that'll work. Compute parsed list tuple int returns an int. I'm just clobbering this function so that this will be the one that runs instead of that upper one up there. We're actually going to use a lot of the same idea here, but instead of having Z3 just guess this, we're going to try and loop over as many n's as possible until we get to a value that's correct. So we're going to start by checking n equals 0, then n equals 1, then n equals 2, then n equals 3. And it turns out this is actually fast enough to solve this problem. So we're going to follow a lot of the same pattern. T equals 0, mults equals parsed 0, 0. And then for bus, comma, pause in parsed 1 colon. And we really only need to check this here. So we need to check if t mod t plus, wait, how does this work again? T plus this position mod by bus is equal to 0. If that's true, then we know we've gotten an answer for that sub part of the problem. So we can say while t plus position mod bus is equal to 0, or is not equal to 0, we need to add in that multiplier over and over. We need to iterate this, increase this n repeatedly. And we can do that by doing t plus equals mult. So that'll just increase this n until this problem is solved here. And again, once we found that right n, we need to increase our multiplier, and you can do that by doing mult times equals plus. And then finally, you return t. And so this is kind of the, I'm not as smart as Z3, or I'm not as smart as Z3, but I can just brute force increase this number until I satisfy the solution. And if we run this now, you'll see we get the same set of answers here. But the way that I actually solved this on stream is somebody gave me a hint that this is actually a sub-problem of the Chinese remainder theorem, which I learned in school a long time ago, but I've since forgotten because I literally would never use it in actual practical programming. But this is almost exactly the Chinese remainder theorem. And I didn't know how to implement the Chinese remainder theorem, and I didn't want to think about the mathy parts of this. So I just installed a library which implements it for me. And if you do pip install sympy, that is the library that I used, I need to actually grab the import path out of there to figure out what... sympy is a really, really big library. To figure out the day 13 part 2, to figure out the function there. So, this implements the Chinese remainder theorem for us, so we don't have to think about it. And so let's make a third function here that implements that uses CRT to solve this. So compute parsed list tuple int returns int. And for this, we really just have to take our bus IDs, which are kind of our moduluses, and their positions, which are going to be their initial values. And we actually need to subtract one because the equivalence here is, say that this is the equivalent symbol. It's actually t plus offset is equal to, or yeah, is equivalent to, what is it? Wait, what? What is the equivalent supposed to be here? The equivalence ends up being t is equivalent to negative offset mod bus ID. Oh yeah, then it would just be this. So we have to convert the offsets into negatives. But anyway, we get the mods equals bus for bus this in parsed, and offsets equals negative offset for offset in parsed. And then if we call CRT on this, we get red and some other value. This is the n that satisfies the problem. CRT mods offsets and then return red. I think this is the CRT solution, but again, it kind of hides away the actual problem there. Offset is undefined. Offsets. Yeah, and you can see that CRT returns the right answers for us. But again, I don't understand the Chinese remainder theorem. I don't quite understand all of the theory here, but that's another way to solve those. If we look at algorithmic efficiency here, it's actually really, really difficult to talk about algorithmic efficiency, especially because the Z3 solver is a complete black box, so I don't know what's going on here. And this is, I'm not sure what it's bounded on. My guess is that this is somewhere near n squared, but I actually don't know, and I would have to think about it a little bit more. But Fortunately, the n is pretty small. It might actually be n factorial because it's the worst case you would be multiplying all the numbers together. But again, I don't know. So I'm not going to comment on the algorithmic efficiency here. But anyway, this is kind of 3 different ways to solve it. Hopefully this gave you a better view of how the problem is organized and, you know, how the periodicity plays into this. But this was definitely like a big brain hurt when I was trying to implement this live. But anyway, thank you for watching, and I'll see you for the next day.